Here's the complete story of how the Chernobyl nuclear plant exploded. The Chernobyl plant used a graphite-moderated boiling water reactor. The reactor sat inside a compartment with walls over 8 feet thick. Inside the sealed shell, more than 2,000 graphite blocks were placed. The graphite blocks act as a neutron moderator to better sustain the chain reaction. Each graphite block has a vertical channel running through it. Inserted into these channels are the nuclear fuel rods. Stacked inside each fuel rod are uranium pellets made from U-235. When a neutron strikes uranium-235, the atom splits into 2 lighter nuclei. At the same time, it produces 2 to 3 neutrons and releases enormous heat. Those 2 or 3 neutrons then react with other uranium-235 atoms. This forms new fission events. This fission reaction keeps going on and on. That's how a fission chain reaction forms. In the end, it generates a tremendous amount of heat. If the fission reaction can't be controlled, it can lead to catastrophic consequences. So to control the fission reaction, the other graphite blocks also have a large number of control rods inserted into them. These control rods are made of boron. When the control rods are inserted into the reactor, large amounts of neutrons get absorbed. The fission reaction then slows down. When the control rods are pulled out, the neutrons increase again. The fission reaction then ramps up sharply. At the bottom of the reactor, there are many cooling water pipes. Cooling water flows through these pipes. As it passes through the core, this cooling water gets heated by the fission reaction. The enormous heat brings it up to its saturation temperature. This heated water then evaporates. The steam and water mixture is then sent into the nearby steam separator. The separator splits the steam from the water. The separated steam travels down along the pipes. Eventually, it reaches the turbine units. The steam first passes through the high-pressure turbine. Then it reaches the low-pressure turbine. This drives the turbine's shaft to spin at high speed. The spinning shaft then drives the generator behind it to rotate. And that's how electricity is generated. The spent steam is then cooled by the condenser beneath the turbine units. The cooled water travels through pipes back up to this position. After some treatment, this water travels along the pipes to the pumps here. Finally, it gets pumped back to the bottom pipes of the core. And that completes the full loop. Now we understand the basic principle of the reactor. Next, let's look at why the reactor exploded. On April 26, 1986, plant workers planned to run a test. They wanted to check the reactor's safety performance during a power outage. So following the test requirements, the workers took the reactor's thermal output and slowly lowered it to half power. But Kiev was at peak electricity demand at the time. The plant was told to pause lowering the reactor's power. So the test got pushed back more than 10 hours. The time came to around 11 p.m. that night. The more experienced day shift workers were replaced by the night shift. The problem was the night shift had nowhere near enough experience handling problems. And that's where the danger started to take root. At the same time, the reactor itself was harboring a hidden danger. Because the reactor had been running at half power for more than 10 hours, the fission process had produced a large amount of xenon-135. Xenon-135 grabs the neutrons that trigger fission. This left the reactor with too little reactivity. This phenomenon is also called xenon poisoning. Xenon poisoning dropped the reactor's power to just 1% of what it was before. But to reach the power level needed for the test, the engineer in charge of the test at the time decided to pull out the vast majority of the control rods. This was meant to speed up the fission reaction. A few minutes later, the reactor's power rose slightly. But the power was still far below the test level. So the night shift shut down 2 more circulation pumps. This slowed down the flow of cooling water. They also manually removed even more control rods. In the end, fewer than 10 were left. This series of reckless moves made the reactor extremely unstable. The reactor's power began to spike rapidly. Seeing that something was wrong, the shift supervisor, Akimov, quickly hit the emergency shutdown button. The control rods that had been pulled out were inserted back into the core. If we look closely at a control rod, it's actually split into an upper and lower part. The boron in the upper part limits the fission reaction. The lower part is graphite. When the control rod is pulled out, the graphite fills the gap left behind by the boron. Since graphite acts as a moderator, it speeds up the fission reaction. The original intent behind this design was good, but because they had pulled the rods out earlier to boost reactor efficiency, the control rods were withdrawn too far. In other words, they were pulled all the way to the top. When the control rods were emergency inserted, the graphite tips entered the core first. Since graphite speeds up the fission reaction, that sudden insertion actually drove the reactor's power, shooting up to 33,000 megawatts all at once. That was more than 10 times the reactor's design power. It caused the bottom of the reactor to start melting. This blocked the control rods from going in any further. That made the fission reaction impossible to control. In the end, the reactor went completely out of control, and it finally triggered a massive explosion. The blast flipped the reactor's 1,100-ton lid right off. More than 55 tons of radioactive material spilled into the surrounding area. That night, the radiation level in the town of Chernobyl reached 600,000 times the normal level. That's equal to the radiation from dozens of atomic bombs going off. To stop the nuclear contamination from spreading further, a huge number of rescue workers rushed to the scene, but they simply couldn't get near the reactor. A team of experts made up of Soviet engineers proposed 3 solutions for this. The first was to fill the reactor with sand, but that would make the neighboring reactor number 3, which hadn't exploded, impossible to access. It might even collapse. The second option was to pour concrete into the reactor to seal it off. But the exploded reactor number 4 was built on loose soil. The enormous weight would make the reactor sink. It could contaminate the groundwater. It might even cause an even larger thermal explosion. In the end, the engineers chose the third option. That was to seal the entire reactor inside a sarcophagus. This option had one advantage. It wouldn't disturb the reactor, which had already stabilized. But building the sarcophagus required cranes and heavy trucks to enter the site, and the area around the blast site was covered in radioactive debris. So armored vehicles fully wrapped in lead were sent in to clean up the debris at the scene. In spots the armored vehicles couldn't reach, like the rooftops, small robots handled the cleanup. But the robots cleaned very slowly. Within minutes, the extreme radiation would burn out the robot circuits. But to build the sarcophagus, the rooftop had to be cleared. So they had no choice but to send people in. But inside the reactor after the explosion was the deadliest place on Earth. Despite the enormous risk, thousands of people still put on radiation protection gear and were sent up to the rooftop to work. At the same time, around the reactor, workers laid down a large number of concrete blocks on the ground. This was to keep the soil from getting contaminated further. Because the exploded reactor number 4 was connected to reactor number 3, the two were separated by a massive concrete wall. To isolate reactor number 4, thousands of workers had to cut through a large number of pipes. And they had to rewire and reconnect everything. And all of this had to be done in a high radiation environment. Afterward, workers set up a large number of steel cages around the reactor, and they poured concrete inside them. This formed a concrete wall. This concrete wall offered the workers a certain level of protection. Next, construction vehicles started moving in to build the sarcophagus. But the construction required oversized prefabricated steel plates. They would be used when pouring the concrete walls. To lift these prefabricated steel plates into place, the Soviets bought the 3 largest cranes in the world at the time from Germany. Because the cranes were so heavy, in order to transport them to Chernobyl, every bridge along the route had to be reinforced beforehand. After that, workers began using concrete trucks to haul concrete near the reactor. To protect the drivers, the cabs of the concrete trucks were converted to lead-lined shells. Then the workers poured the concrete in layers, building the sarcophagus one layer at a time. The other side of the reactor was enclosed using prefabricated steel forms up to 130 feet tall. A large amount of concrete was also poured inside them. In the end, this ring of walls used more than 14 million cubic feet of concrete. After the walls were built, the next thing to build was the roof. But there was a very serious problem here. The explosion may have damaged the building structure of the original roof. If they built the roof directly on top of it, all their work might be wasted. It could even cause another explosion. So to figure out how badly the structure was damaged, engineers designed a special inspection device. The inspection device was made from 25 tons of lead. An observation window was left on top of it. Then a volunteer would climb inside the device. A crane would then lift it to the top of the reactor. This let them carefully inspect the extent of the roof damage. At the same time, to make nighttime work easier, an airship equipped with a 40-kilowatt floodlight was placed above the reactor. This made it easier for workers to do their jobs. While the volunteers were inspecting the roof, they found 2 ventilation shafts had survived the explosion. So workers poured concrete into these 2 ventilation shafts. On the other side, there were 2 sections of wall still standing. With these supports in place, they could begin building the roof. The sarcophagus roof used I-beams. They were pre-assembled in a safe location. Then they were transported over, and a crane was used to lift them. But the crane's maximum lifting capacity was 159 tons, and the weight of the I-beam was already over 159 tons. So when the I-beam was lifted, the back of the crane was lifted more than 3 feet off the ground. But the crane didn't tip over, so the workers immediately added 40 tons of counterweight to the back of the crane. Finally, the crane returned to the ground. After that, the I-beam was set onto the supports prepared earlier. At the same time, on top of the I-beams, workers placed many large pipes. The original idea was to pour concrete inside the pipes, but because it would add extra weight, they didn't pour it in the end. Next, a layer of steel trusses was added on top of the pipes. Then a thick layer of radiation shielding panels was laid down. But the left and right sides were still open, so workers added 3 crossbeams on one side and 1 crossbeam on the other side. At the same time, they covered the top with radiation shielding panels. After the main body was completed, there were still some lightly damaged sections of roof nearby. Here, workers set up support frames and crossbeams, and they covered them with radiation shielding panels. After several months of hard work, the sarcophagus was finally completed. But the sarcophagus was not permanent. Its design lifespan was only 20 years. After 20 years, it might face collapse. So engineers later added an even larger sarcophagus over the outside of it. A large crane was installed on top of the new sarcophagus. It can dismantle the old sarcophagus and the reactor wreckage. The Chernobyl plant explosion was the worst nuclear disaster in human history. The loss and destruction it caused are already impossible to measure. It also serves as a constant reminder to humanity that safety is never a small matter. Only by respecting the rules can technology truly serve humanity.